AP Chem. This is Unit 9 review, last unit review of the year. Must be excited, AP exams coming up, and you're probably cramming all of my videos for some extra, just to be sure. So, Unit 9, you're going to be learning about delta S, delta G, G, and E naught. So, let's get started, shall we? Alright, first off, 9.1 and 9.2. This is basically just introducing you to the concept of entropy. So basically what entropy is, it's basically sort of like the dispersion of a system. So like if I have a box with a bunch of particles here, the the particles could all be in like this one corner kind of clumped together, and this will be low entropy. However, if I have that same system, but like after a little bit of time, uh, these clumps will probably all move away from each other, right? Sort of like in a random configuration. Not a torus. Or an Aries, whatever it is. This is high entropy. Delta S low, S not low, S not high. And so, in order to calculate the standard entropy of formation or of reaction of something, we just take the initial and final. We just take the final minus the initial state. So, delta S naught would be equal to S naught products minus S naught reactants. Now, as a general rule of thumb, for entropy, solids have less entropy than liquids. Liquids have less entropy than gases. Additionally, more gas on one side means that it has more entropy on that side. Less gas, or even a different state, will usually mean it has less entropy. So let's do an example, shall we? Calculate the sign of delta S for the combustion of hydrogen to form water. 2H2 plus O2 turn to H2O. Calculate the standard entropy of this. Well, the sign of it at least. You will note that both of these are gases, and this is a liquid. Just pause if you need time, or just let me explain it in a couple seconds. Alright, so you'll remember that gases always have higher entropy than liquids, and usually higher amounts of gas will mean more entropy. So delta S naught in this case would be negative, which means that overall, if you're looking from an entropic standpoint, this reaction is non-favorable. However, entropically is not the only way that we can look at things. Introducing the units, the subunits of 9.3, 9.4, 9.5, 9.6, 9.7, and 9.9. Now, these are all going to deal with one specific concept in general, and that is delta G. Or delta G naught, as many AP problems will suggest. So, delta G is kind of basically like the free energy of it. In fact, it is the free energy of the system. It's called Gibbs free energy. And basically, it allows you to tell whether a thing will happen, if it will happen, basically. It can't tell you whether or not it will happen in your lifetime, but it can tell you whether or not it will happen. Basically, this boils down to just delta H minus T delta S. And so, basically, if we draw a table here of delta S, delta H, and the outcome, remember that we want delta G to be negative because that's when it's favorable. So if delta H is negative and delta S is positive, then the outcome is negative for all temperatures, and you basically don't have to worry about it being favorable at that point. If delta H is positive and delta S is negative, then it's always going to be positive at all temperatures. and so it's not favorable at all temperatures. Now, where it gets interesting is when delta H is positive and delta S is positive. Then this is negative only at high temperatures. Or delta H is negative and delta S is negative. This is only negative at low temperatures. So there's kind of like a big caveat here, right? So, you can, on one hand, you can have an exothermic reaction and a positive entropy change, but that almost never happens. On the other hand, you can have an endothermic reaction and a negative entropy change, but that also almost, well, never happens. What you're really going to be dealing with is the last two cases, where both the delta H and delta S are positive or negative, and you have to figure out where is it going to be favorable. Is it going to be favorable at the temperature you're given? You're going to have to calculate that. It's just what AP wants. So now, basically, back to what I said about being able to tell whether it's favorable or not, you really can't tell if it can happen in your lifetime. For example, carbon graphite to carbon diamond is technically, I think, a favorable process. However, you're not going to stare around a pencil lead all day and hope it turns into diamond. That's a futile effort. In fact, this can really only happen at very high pressures and temperatures. So, really, this will basically never happen, and this is what is known as kinetic control. So, delta G may be negative, but that doesn't mean that the little k in the rate laws will allow it. Right? Because it could have an extremely high EA, or it could just have, like, a bogus amount of steps that also have high EAs. So, now we can move on to connecting this unit to all the other units so far, except for 1, 2, and 3, which is basically just the basis of chemistry. So, how do we connect this with unit 7? Simple. We introduce another equation. Delta G naught is equal to negative RT ln K. K in this case being the equilibrium constant. Now there is another variation of this equation. Delta G delta G non-standard is equal to delta G standard minus plus RT ln Q. Now the basic premise here goes that when Q equals K, then delta G equals 0. And so you can get the first equation by deriving it like that. Additionally, we can kind of connect it to the thing that's going to be later introduced here, electrochemistry, which again we introduce another equation, delta G naught is equal to negative NF E naught. And you're wondering why I don't use capital E like the textbooks. This is what is known as epsilon. I believe it is technically the correct term for E naught, not capital E, epsilon. However, most AP textbooks will tell you that it's capital E, so for all intents and purposes, epsilon and E naught and capital E are basically just the same thing. So now let's do an example with all this newfound knowledge in your head. So, say you have a reaction with delta H naught equals positive 40 kilojoules per mole, and delta S naught is equal to positive 150 joules per mole, Kelvin. So, is this favorable at 298 Kelvin? So, you can either solve it yourself by pausing the video or wait for me to explain it in like a couple seconds. Alright, so again, we're going to use delta G naught equals delta H naught minus T delta S naught. And so we can calculate our, values. What you're gonna want to realize, though, is that you can't simply add kilojoules to joules. They're different units. What you're gonna want to do is you're gonna want to convert joules to kilojoules or kilojoules to joules. I like to convert kilojoules to joules because it seems like a much nicer method, and you don't have to deal with a lot of the decimals. So what we can do is we can set delta H equal to positive 40,000 joules per mole. And now we can solve for delta G. 40,000 minus 298 times 150, which is equal to 298 times 150 multiplied by -1, and add 40,000. You get negative 4,700 joules per mole. Now, this is usually going to be converted to kilojoules per mole, which is negative 4.7 kilojoules per mole. Now, you can see that this is actually negative, which means that delta G naught is favorable here. However, when is it not favorable? Like, there has to be some temperature, since both are positive, at which delta G becomes positive instead of negative. Well, we can calculate that by setting delta G equal to 0. So what setting delta G equal to 0 means is that we can set delta H naught equal to T delta S naught. And here we can solve for T by saying T equals delta H naught over delta S naught by algebra. Which we can say 40,000 over 150, which is equal to 267 Kelvin. And again, we always use Kelvin because Kelvin is the absolute temperature scale, and you don't want to be working with negatives when you're already having negative in mind. So now we can get to the second part of this unit, electrochemistry. Okay, you've all probably heard of a 9-volt battery. It has 9 volts, and it has multiple chemical reactions going on inside it. Well, this is how electrochemistry can come up, right? If you have a 9-volt battery that's basically dead, but you still want to use it, you can probably use electrochemistry to recharge it and get it back to new. Or some other kind of battery that you want to recharge. Your phone battery is a great example. Basically, every computer battery, your car battery, is a great example of electrochemistry. So now, what is electrochemistry? It's basically the study of, like, everything electricity that has to do with chemistry. So, the very basic unit is a galvanic cell, which I will draw for you right now. And then here's a wire. Here's your solution. I know, top tier drawing. And then here's where it gets important. Notice what I just drew. This is what is called the salt bridge. And it is the most important aspect of an electrochemical cell. What this allows the cell to do is basically allow it to balance the charge as it goes, right? Because of course, when you're reducing and oxidizing stuff, you're obviously going to accumulate positive and negative charges, which can be bad when you're trying to, well, identify the charge of the cell. So basically what this does, you have a half cell called an anode, another half cell called a cathode, and salt bridge in between them. Now, what you can always do is remember the acronym NOx red cat. And this will help you remember the anode has oxidation, and the cathode, that's the cat, has reduction. That's the red. So, what you can always remember, NOx, red anode has oxidation, reduction happens at the cathode. It's dumb, I know. But what really happens is your brain remembers the dumb things. So, this will help you ace your AP exam, which isn't meant to be aced. So, what you can do here is basically just kind of trial and error stuff, right? Or you could look up an E naught table, which is probably already given to you in the AP exam. So, basically, E naught is the standard cell potential that it has versus hydrogen, which is defined 0. Hydrogen's kind of difficult to measure against, I'll be honest. But you can always use another standard and compare it to and use it to compare hydrogen to it by doing some complicated math. So basically, this is the cell potential and is measured using a voltmeter or a multimeter, whatever you have on hand. Right? So this is the basic unit for electrochemistry, but it's not the only unit. You can also have an electrolytic cell from the word electrolysis. Not Y-S-I-S. So basically what electrolysis is driving a reaction, a non-spontaneous reaction, delta G greater than 0, with a spontaneous reaction, usually with a battery. So keep in mind, you're not going to be asked to label a battery on the AP exam. That's just dumb. So what you have here is like your metal, your solution, another metal, and they're connected via a battery. I know, terrific drawing. And so this kind of is just the basic electrolytic cell. Now, this is where coupling comes in. A concept from 9.7 that I would have forgotten to cover. However, it comes in right now. So a coupling is basically using delta G naught being less than 0 for a process and driving a delta G naught greater than 0 for another process. A great and what you can actually do here is use Hess's law or some analog. So if you remember, Hess's law is if you have a delta H naught reaction that you're trying to find, you can always break it up into separate reactions that you're given, which is equal to the sum for any reaction of delta H naught N all the way to whatever your I value is. It could be 10, could be 100, we don't know. This actually works for all state functions, and delta G naught is a state function, so you can say delta G naught reaction is equal to the same notation, the sum of all the reactions with their respective delta G's for a certain amount of reactions. Could be 2, could be 10, we don't know. So again, we have connected Unit 9 with Unit 6. We've connected Unit 9 with Unit 7. Unit 9 presumably already connects with Unit 8 since it comes right after, and a lot of the concepts from Unit 8 can transfer into Unit 9 really nicely. Kind of. I mean, you have Ka, you can calculate delta G naught of the dissociation of an acid and a base. But moving on back to electrolysis. And then there's a famous physicist named Faraday who comes along. Faraday looks at the electrolytic cell and says, well, I wonder if I can translate that into mathematics. So he does. And this is where we get, probably very well known, I equals Q over T. I, in this case, is current. Q is charge. And T is time. So basically what this says is that the current is equal to the charge over time, which is the exact definition used in physics. So now, let's go ahead and do something with it. We are given that 2.5 amps is passed through a solution of copper 2 plus ions for 30 minutes. How much grams of copper metal is deposited? And now you can always pause the video, or you can probably just wait for me to explain it in a couple seconds if you're, like, really lazy. Alright. So what we're really going to want to do is convert 30 minutes into seconds. Because the proper definition of an ampere is 1 coulomb per second. You can't really use minutes here. This isn't kinetics. So what we can do is we can say 30 times 60, that gets us seconds, and multiply that by the charge, the current that we're given, and we get 4,500 coulombs. Now, what Faraday discovered was that 1 mole of electrons has a charge of 96,500 coulombs. And so what we can do here is we can find the moles of electrons that pass through the circuit. We divide that by 96,500, and we get 0.0466 moles of electrons. So then we can always just write the chemical equation Cu2 plus 2E turned to Cu. And again, we see 2 moles of electrons per 1 mole of copper, so we divide by 2. And that gets us 0.233 moles of copper, which you can then multiply by the molar mass to get mass of copper. I just so happen to know that the mass of copper, molar mass of copper, is equal to 63.55 grams. You're going to be given a periodic table on the AP exam. Don't worry about memorizing molar masses. Multiply by 63.55, and we get 1.48 grams. And just quick reminders, okay? Last review video. Remember your signs. Thermodynamics doesn't skimp on the signs, right? Delta H being less than 0 has a completely different meaning than delta H being greater than 0. Remember your electron configurations. PES doesn't screw around. You can have a binding energy question, and if you forget your electron configurations, you're basically losing that point. And again, units. You don't want to be conflating kilojoules with joules, even though they have joule in the same name. You're going to want to convert joules to kilojoules or kilojoules back to joules because they're basically just the same thing, except one's multiplied by 1,000. And remember, salt bridge. I know it seems mundane, but the salt bridge is the key to making a galvanic cell actually go. And in fact, I forgot to give you a calculation on galvanic cells, so we'll do one really quick. Say they have a galvanic cell of silver and copper. In the cathode solution, you have Ag+, and in the anode solution, you have Cu2+. What is E naught of the cell? You can pause for a few minutes, or wait for me to explain it in a few seconds. Alright, so E naught cell is equal to E naught of the cathode minus E naught of the anode. And so what you can do is you can look up the table that you're probably going to be given for E naught, for both E naughts. And here's where things get interesting. Where with delta G or delta H, you would need to multiply by the moles of electrons, with E naught you do not. I happen to know that E naught silver is equal to 0.80 volts. And I also happen to know that E naught copper, specifically copper 2 plus, is equal to 0.34 volts. So what I can do is 0.80 minus 0.34, and I get that the final answer for our E naught cell is equal to 0.46 volts. And as always, I hope you have a wonderful year. I hope you ace your AP exam, and I hope you ace your test coming up. And for the final time, see you.